Okay, so last week we looked at a proof system, and we proved soundness and completeness. We didn't really prove soundness, but I said it was straightforward, and we have soundness and completeness. And there's a little bit of discussion in completeness about the terminology for the kind of model forms, which I didn't quite remember because I was tired last week. So basically, the proof of completeness I gave is a proof that style of proof is due to Henkin, and the kind of model constructed is a Henkin model. And there was some discussion about also logic programming, and I think in logic programming there's a Herbrand model, and yeah, so this was a Henkin model, not a Herbrand model that we constructed last week. So completeness via construction of a Henkin model. And the nice thing about a proof system is we have these formal rules for reasoning, and we can use those in practice, for example, in proof assistance, if we want to formalize mathematics. But we would never do that using the Hilbert system that we looked at last week, because the rules of proof are too crude and awkward to use in the Hilbert system. Nonetheless, we had a proof system. The proof systems are the basis of one area of logic, a big area of logic called proof theory, which is basically about these proof systems and the properties that their proofs have. One of the other main areas of logic is called model theory, and that's the study of structures, the structures that are models of logical theories, and trying to learn something about those structures and their properties from the fact that they're models of logical theories, and from using that logical techniques with them. And so last week, having looked at essentially proof theory, well, proof systems under kind of soundness and completeness is giving a relationship to model theory, because it's giving a relationship to structures. We're going to change topic and today go to model theory. And the title of the lecture is called Elementary Model Theory. Which is a little bit of a pun, because it's elementary in the sense that this is going to be basic model theory. It's an introduction to model theory. But also elementary is used as an adjective to describe first order. So this is also the model theory of first order logic, which people sometimes refer to as, well, you don't hear elementary logic so much, you occasionally hear it, but there are various places when people want to talk about first order things, so one just has quantification over entities in the structure that one's dealing with. There are various places that people use elementary instead of first order. And interestingly, the key to our introduction to model theory, the first result we're going to prove, although it's a result from model theory, it's one of the main results of basically the most important basic result in model theory. The way we get it is using the proof system. And in fact, many of the results, not just the first result, but several of the results we're going to get today, we're going to get them via having this proof system and having the soundness and completeness properties. So the proof system, as well as being interesting in its own right, actually gives us a mathematical tool for getting started with model theory. And the first core result we're going to look at is a very famous result in logic called the compactness theorem. So we had last week the notion of a set of formulas being satisfiable. We use the general notion also for formulas with free variables in order to have a nice way of proving completeness of the proof system. For the following lectures from today onwards, it's not usually going to be necessary to look at to talk about properties of formulas, including formulas with free variables. So we'll often restrict properties to sentences. So in the case of a set of sentences, I'll just remind you, we say a set S of sentences is satisfiable if it has a model. In other words, if there exists some structure over the signature that we are forming the sentences from, if there exists some structure that satisfies all the sentences. So if there exists some structure, curly M, such that all the sentences in S are true in the structure M. And the completeness theorem says, stick with the blue on this board, a set of sentences S is satisfiable if and only if every finite subset of S is satisfiable. Every finite subset of the sentences S is satisfiable. It's obvious that if a set of sentences is satisfiable, then not just every finite subset of it is satisfiable, but every subset of it is satisfiable. That's clear, because you've got fewer things to satisfy if you've got a subset of the set of sentences. So the left to right implication is obvious. But what about the right to left implication? So suppose every finite set of sentences is satisfiable. Why is it the case that, so of course this is only an interesting property in the case that S is an infinite set of sentences, otherwise it's trivial. If S is an infinite set of sentences, suppose every finite subset is satisfiable, then how can we build a structure from that fact? How can we build a structure for the whole infinite set of sentences? You know, any finite collection, we can find a structure for them, but those structures might not have any obvious relationship between each other. So, you know, somehow we need to manufacture a structure that's going to model all the sentences simultaneously. And looked at in that way, it seems like quite a hard problem. You can imagine there might be some complicated way of gluing all the structures together or something like that. But if you think about that, you'll realize that's actually very tricky to do it like that. It turns out that the completeness theorem gives us a very easy answer to this question. Well, not answer to the question, but a very easy way of proving this theorem. So a set of sentences is satisfiable if and only if there's some model of that set of sentences. So just by the direction of entailment, by the definition of entailment, and I think I basically wrote something similar last week, S is satisfiable if and only if falsity is not entailed by S. Okay. Yeah, this entailment says all structures that satisfy all sentences of S. Sorry, there should be a not there. Yeah. So if false is a consequence of S, then yeah, all structures that for every structure that satisfies every sentence in S, false holds, but false can never hold in a structure. So that just means there are no structures that satisfy S. So the negation of that is that there exists a structure that satisfies S. Okay, so now for the other direction, with this if and only if, which is immediate from the definition of logical entailment. So we're going to work like this. We're going to prove the contrapositive. We're going to prove if S is unsatisfiable, then there exists some finite set of sentences that's unsatisfiable. So suppose S is unsatisfiable. Well, by this equivalence here, that means that false is entailed by S, is a logical consequence of S. But now by completeness, we have the proof of false from all where the assumptions we use are all taken from the set of sentences S. But any proof only uses proof is a finite sequence of formulas, so it only uses finitely many of the sentences of S. So since the proof is finite, if we take S prime to be the set of sentences used as assumptions in the proof, by defining S prime to be equal to the assumptions in proof, we have that the same proof gives us that false is we have a proof of false from S prime. And now by soundness, that means that false is a by soundness, false is a consequence. False is entailed by S prime, and hence, again by this if and only if S prime, hence we have found a finite S prime, which is a subset of S, that is unsatisfiable. So we've proved that the negation of this implies the negation of this. In other words, the right to left implication holds. Okay, so very, very simple proof, but it shows us the power of completeness. And to show that this is a non-trivial result, I'm going to give you a couple of applications of it. The first is an application in logic itself, and the second is an application in graph theory. And in fact, this result is quite useful in. Yeah, one often finds results in mathematics that can be proved using the compactness theorem, or fairly often. I have nice proofs using the compactness theorem. So, for the first application, would it be possible to find a possibly infinite set of axioms that axiomatize the property that a structure is finite? axioms whose models are exactly finite structures, all finite structures. So we can axiomatize that the cardinality is greater than or equal to 2, for example, using the sentence that we looked at in lecture 3 or 4 or whatever. Anyway, we can axiomatize all the other interesting properties of cardinalities like that. Can we say that, can we find a set of axioms that say that the set is finite? And the answer is no, and it's no because of the compactness theorem. But let's turn it into a positive result. And the positive result is this, that whenever we have a set of axioms in first order logic over any signature, if the axioms enjoy the property that they have, that there exist arbitrarily large finite models of those axioms, then there is necessarily an infinite model of the axioms. And from that, it means we can't axiomatize finiteness. I'll talk you through that in just a moment. Let's define the property. So we say that this is stronger than being satisfiable. It's a set of sentences S. So again, S is a set of sentences, has arbitrarily large finite models if for every natural number n exists a structure M, which is a model of S. So M is a model of S, and the cardinality of its underlying set, ordinary font M, is greater than or equal to N. Okay. So it doesn't need to. Yeah, there can be lots of gaps in the size of the possible models, but the sizes of models have to be cofinal in the natural numbers, and it's, as people sometimes call it. Have to be infinitely many. It's enough to say there are infinitely many different sizes of possible models, finite models. There exists a finite. They're supposed to be finite structures. And the proposition is that if S has arbitrarily large finite models, then it has an infinite model. And so, as a consequence of this, we can't find a set of sentences whose models are exactly all finite structures, because if we had such a set, it would have arbitrarily large finite models, and by definition, it wouldn't have an infinite model. But this result is more that I've stated is more powerful than that. It's giving us a nice condition that we can use in practice often. If we've got a theory, we can see it's got arbitrarily large finite models, and we can then tell that it has an infinite model. Deduce that it has an infinite model. And the proof is really easy from compactness, so this is not going to take very long. The theory or rather set of sentences. It's not a theory in the sense of being closed under logical entailment, but often I'll use theory just to mean a set of sentences here. So we take all the sentences in S, and we simply union that with, and I'll just write commas, so we've got all the sentences in S, and we simply union it with the sentence that tells us the cardinality is greater than or equal to 2. So you'll remember that was there exists an X, there exists a Y such that X is not equal to Y. And the sentence that says the cardinality is greater than or equal to 3, cardinality is greater than or equal to 4, and so on. So we put in one of these for every natural number. Since S has arbitrarily large finite models, every finite subset of, let's call this S prime, or let's call it T. Since S has arbitrarily large finite models, every finite subset of T has a model. Because a finite subset will be stopping the cardinality bound at some finite number, and we find a larger structure. So since S has arbitrarily large finite models, every finite subset of S of T, every finite subset of T is satisfiable. And hence, by compactness, T is itself satisfiable. By compactness, T is satisfiable. And then you see that a model of T is necessarily infinite because we've got infinitely many cardinality bounds. A model of T is an infinite model of S. It has to model S because we've got all the sentences from S are part of T. So a model of T is an infinite model. But the models of T are exactly the infinite models of S. And by the way, although I said we can't axiomatize being finite, if you just look at this part here, you see that by this infinite set of axioms, we can axiomatize being infinite. But by a necessarily infinite set of sentences. Okay, so that's the first application. Arbitrarily large finite models means we have an infinite model. The second application is more mathematical. And this is a theorem that was sufficiently interesting to have a name. So in this department, discrete mathematics is quite a major area, and there are some very good researchers in graph theory, and a lot of graph theory is just about, people often take it to be about just finite graphs, but there's also an interesting graph theory of infinite graphs, which belongs to a field known as infinite combinatorics would be related to that. Anyway, this theorem is a theorem about infinite graphs, and has a name. So it's a theorem that was published by De Bruyne. For those who know something about lambda calculus and formal implementations, I've actually got no idea if this De Bruyne is the same De Bruyne that is the De Bruyne of De Bruyne indices. All I know about this De Bruyne is that his Erdős number is 1. And I know that because this is a theorem of De Bruyne and Erdős. So if you know Erdős, the very famous prolific mathematician. Anyway, so they thought this was interesting enough to publish, but it's just a very simple application of the compactness theorem. They knew some logic. So the theorem says if every finite subgraph of an infinite graph has a k-coloring of an infinite graph G, has a k-coloring. So k is some number here. I'm going to write colouring in the British English way with a U. Then G itself also has a k colouring. Okay, so we're going to prove this theorem using compactness. I'll remind you briefly, what the various terms mean. I'm going to remind you what the various terms mean in a way that relates it directly to logic, so that we can apply compactness. So firstly, what is a graph? A graph is simply, well, a graph is a set of vertices and a set of edges, and a simple graph, which this is about simple graphs. These are the non-directed graphs, undirected graphs, in which you don't have any little simple loops, so no vertex is directly connected to itself. So in other words, in logical terms, a graph, a simple graph, let's write simple, but a simple graph is a model for the theory with the signature E, where E is the binary relation symbol, meaning the edge relation, over the signature E, binary relation symbol, with the axioms that for all x, where x ranges over vertices, make it undirected first. So if there's an edge from x to y, then there's an edge from y to x. It's undirected. And secondly, for all x, it's irreflexive. So there are no simple loops. There is no loop for all x. There is no loop from x to x. Simply that. That's all a graph is. And what's a k-coloring? Well, a k-coloring of G, a model like this, is an expansion of G in which we interpret some extra predicates, is an expansion of G, which simply means adding some more predicate symbols to it, with unary predicates, C1 up to CK. So these are k different colors. And remember, intuitively, a k coloring is an assignment of k different colors to vertices. So each vertex gets exactly one color. So that whenever you have an edge between two vertices, then the colors of those two vertices are different from each other. So So we have unary predicates K for the colours of vertices, and the axioms they need to satisfy are for all X, every vertex has exactly one colour. So for all X, C1X or all the way up to CKX, well, that's saying every vertex has at least one colour. To say it has exactly one colour, we need to say for all X, it's not the case that CIX and CJX when I is different from J. So for every pair of distinct colours, we have that axiom. Right, so that's saying every vertex gets exactly one colour, and then we need to make sure that no two adjacent vertices get the same colour. So we also have for all X and Y, if there's an edge from X to Y, then it's not the case that C1X and C1Y, and it's not the case that C2X and C2Y, and so on, and it's not the case that CKX and CKY. Okay. Is this clear? So if we have a structure satisfying these, a structure in the relations E and C1 to CK satisfying these axioms, then what it amounts to is a simple graph together with a K colouring. Okay. To the statement of the theorem, suppose we've got a graph, an infinite graph, and every finite subset has a K colouring, then the graph itself has a K colouring. So this should, just thinking about it, it already reminds us of compactness in the way that I was describing compactness before I gave the proof using the completeness theorem. I said, well, thinking about this, suppose every finite subset has a model, then, yeah, the problem is we need to find a model for the whole set of sentences, and it's not obvious how to be able to combine the different finite models to give us a model for the whole set of sentences. There's exactly the same, the reason this is not a trivial result is that exactly the same problem arises here. Suppose we've got K colorings for every finite subset, then, okay, for every finite subgraph, then each subgraph is determined by a set of vertices. We can K color those vertices, but if we consider a larger finite subgraph, we might have to color them in a different way in order to K color that larger subgraph. And once again, there's no obvious way to combine different colorings of finite subgraphs into a coloring of the infinite graph. So it seems very related to compactness. And indeed, we can now prove it using compactness. So, let's maybe rub off the statement of the theorem. Theorem. So let's suppose we've got a graph. Suppose G is such that every finite subgraph has a coloring. And we consider a logical theory. So consider the theory let's again call it T, axiomatized by the graph axioms plus the A-coloring axioms plus axioms that tell us which graph we're talking about. So those axioms are axioms of the form E, CV, CV prime, where VV prime is an edge in CV prime, or we add a constant for every vertex we add to the signature a constant for every vertex in the graph G to our signature. So add constants CV, so the set of constants CV for every V vertex in G. So we add, and we'll, yeah, that's it. That's all we need to do.
Isn't this a little ambiguous with the notation we just introduced, like with the
what?
Well, we also have like the unary predicate C symbols.
Oh, I see.
Yes.
Well, but these are
capital
capital C's,
okay.
And these are little C's. These are small letter C's. I hope you can see. So we'll keep it like that. But you are welcome in your handwritten notes to use whatever letter you prefer for this. You could use a K for Constanta if you want. Okay, so this is our theory, T, and it's obvious that every finite subset of T is satisfiable because every finite subset of T will only contain information about finitely many edges, and it's then satisfiable by coloring the relevant subgraph. Of course, you might have even dropped some edges, but that just makes the task easier. So every finite subset of T is satisfiable by the assumption here. By the assumption. Hence, T is itself satisfiable by compactness. And if T is satisfiable, if we have a model of T, then that model gives us, obviously, by the definition of the theory, gives us a K coloring of G. We just read it off from the K coloring of G from the colors, the predicates for each of the colors, which predicates hold in the model for the constants that correspond to the vertices. So a model of T gives us a K coloring of G, so let me just make it specifically color V with color I. Not written nicely, but this color is a verb and this color is a noun here. Yeah, in Slovene you would see that more easily, but I mean, it's still the same root word, but you would see it more easily from the declension and conjugation, respectively. Anyway, so we colour V with colour I if C in the structure, if Ci of little cv holds in the structure. And we're done. Okay, any questions on that? That seems an appropriate stopping point. So the reference will be the clock on the back wall, as usual. It's 3 minutes to, so we start again 12 minutes past by the clock on the back wall. Okay, so actually one remark on the proof of the De Bruijn-Erdos theorem. So that if an infinite graph, if every finite subgraph is k-colorable, then the infinite graph is k-colorable. It's actually a little bit of overkill to translate that problem into first order logic. It was convenient because I used the first order axioms to define what a graph was, but it's unnecessary. The same theorem can be deduced as a consequence of the compactness theorem for propositional logic. So you can actually encode the reduction from a graph to logic. You can encode that as propositional logic. So all we need really there is the compactness of propositional logic. The compactness of propositional logic can similarly be proved as a corollary of a completeness result for a proof system for propositional logic, which could just be the very proof system we've been using for first order logic, just restricted to propositional formulas. So propositional logic, we just have propositional constants and the logical connectives. In that case, so even in that case for a general infinite propositional theory and infinite signature, compactness and completeness both require the axiom of choice to prove them. Actually, not the full axiom of choice, but a result known as the Boolean prime ideal theorem. And this result, this application that we had to the De Bruijn-Erdos theorem, I think the De Bruijn-Erdos theorem also likewise requires some choice to prove that for an arbitrary infinite graph. In the case of a countably infinite graph, no choice is needed, and indeed last week we had a proof of completeness for the countable case of completeness that did not use the axiom of choice. Okay, so compactness is our first basic result from model theory. The second basic result is another very old result, which goes by the name of the Löwenheim-Skolem theorem, named after two logicians. There's the Löwenheim-Skolem theorem. The umlauts on. So I'm going to give essentially the original version of the Löwenheim-Skolem theorem first, but there are many modern day variants that are more powerful, and we'll see some of those later in the lecture today, and actually one of them next week. But the original one is very simple. So it's, suppose S is a set of sentences over a countable signature. So it can be an infinite signature, but it has to be, if it's infinite, it has to be countable, countably infinite. If S has a model, so if S is satisfiable, in other words, has a model, then it has a countable model. And it's just that. If you've got a countable signature, you can't axiomatize uncountability. You can,
Excuse me.
yes?
Is this sometimes called the downward Löwenheim-Skolem theorem?
This is even more basic than the downward Löwenheim-Skolem theorem. So we shall come later today to what the downward Löwenheim-Skolem theorem is. It is a consequence of the downward, of what is nowadays called the downward Löwenheim-Skolem theorem. And this is pretty much the original Löwenheim-Skolem theorem. And I'm putting this one first because, like with compactness, we have a very, very simple proof of this, even easier than the proof of compactness. So the proof is, so suppose S has a model. So it's satisfiable. So again, we basically do the same sort of thing we did before. So that means that false is not a consequence of S. So by completeness, hang on. By soundness, we can't prove false from S. So now we apply the completeness theorem, and okay, that says it's satisfiable, so we get back to where we started. But rather than that, we apply the proof of the completeness theorem, and we take the Henkin model that we constructed last week in the proof of completeness. So the proof of completeness for last week for S. And you remember from last week, the underlying set of the model we constructed was equivalence classes of terms. Gives us a Henkin model for S whose underlying set is terms modulo provable equality, essentially. Well, let's just say modulo some equivalence relation. But because the signature is countable, there are only countably many terms, and then we're quotienting terms by an equivalence relation, so there are only countably many equivalence classes, so the model is countable. Since the signature is countable, it's countable. There are only class many terms, hence countably many. So just write aleph 0 many, it will be quicker. Countably many equiv classes, i.e., I won't bother to write it. That is the model is countable. So again, completeness gives us what we want. So this result, when it was first noted in the very early, so even before Gödel had proved completeness, people had some idea of how first order logic worked, and I think Löwenheim was even before 1920, and Skolem was in the early 1920s, and they sometime around then, so it's before the completeness results, they basically understood this situation and were very puzzled by it, and Skolem articulated his puzzlement in what is known today as the Skolem paradox. So this is, so rather than a mathematical application of the Löwenheim-Skolem theorem, we'll have mathematical applications of the more modern versions. Rather than the mathematical application, we're going to have food for thought that follows from the Löwenheim-Skolem theorem, and this is the Skolem paradox, which is the following troubling situation. So we know that we can axiomatize set theory, like the set theory that we do mathematics with, using first order axioms. I never wrote them down on this course, but you know, there are basically 10 axioms for set theory, although some of them are schemas. So you know, basically infinitely many first order axioms, but there are 10 patterns for axioms. So we can give first order axiomatizations of set theory, or their axioms or set theory. So, for example, many people would choose ZFC, so another Frankel set theory with choice for their first order axioms. One hopes that the axioms are consistent, because otherwise people will get worried, and we'll have to rescue mathematics to find out where the source of the problem is. But hopefully these axioms are consistent. And later in the course, when we come to Gödel's second incompleteness theorem, we're going to find out how difficult it is to ascertain if a theory is consistent or not. So hopefully these axioms are consistent. And because they're first order axioms, if they are consistent, that means there's a model. And by the Löwenheim-Skolem theorem, there is then a countable model for set theory. So hence have a model. So by the Löwenheim-Skolem theorem, so the signature is definitely countable for set theory. It just contains one binary relation symbol, the membership symbol. That's all you need in the signature. So by the Löwenheim-Skolem theorem, ZFC then has a countable model. And because you can construct because in set theory you can define the set of real numbers, it includes within it the set of an element that is the set of real numbers, which includes an element in the model representing the set of real numbers. However, ZFC proves that the real numbers are uncountable. ZFC, consequence of the ZFC axioms that R is uncountable. So how can we have a countable set living in, an uncountable set living in a countable model? So that disturbed Skolem, and he posed that to the world, and that can be, it's something for you to think about if you like. So let me just tell you, there is really no paradox, because it's true that if ZFC is consistent, then it has a countable model. It is also true that there is an element in that model that represents the set of real numbers. If the ZFC defines a set, a uniquely characterized set that is the set of real numbers, that's exactly one element of this model. It's also true that ZFC proves that R is uncountable. But what that means, as ZFC proves it, that means from the perspective of that model itself, of this countable model, the real numbers will be uncountable, because we'll have in this countable model, we have an element that represents the set of real numbers, we have an element that represents the set of natural numbers, And we also have an element that represents all functions existing in the model from the natural numbers to the set of real numbers. And it will be true that in that model, the set of surjective functions from the natural numbers to the real numbers is empty. From the outside perspective, we can see that we've got a countable model, and that those real numbers only have countably any elements. But from inside the model, there is no function enumerating those elements. So there is no contradiction here. The real numbers is uncountable from the perspective of inside the model, but from outside the model, looking at the model is countable, and that set is an element of the countable model, and there will be countably many elements in that countable model that are elements of that set. Yes, Gregor?
Excuse me, wouldn't I understand the paradox, but wouldn't it be more concrete to point out not that the set of real numbers is an element within the domain of discourse, but from the perspective of model theory, the entire universe of sets will be a set from the outside perspective. And
that's also true.
Yes, and the set of real numbers will be its subset. And the paradox is that if we have a subset which is uncountable, the enveloping set also must be. So from the paradox as it is written down, I don't see the paradoxality, I guess.
Well, that's good, because there isn't a paradox. The paradoxicality, yeah. So, yes?
We relied on compactness to get the proof of the Skolem theorem.
Well, we use completeness, and we use completeness to get. We don't specifically need compactness itself, but it's all much. It's hard to distinguish between them because they're all basically related, very closely related to each other. We use completeness for both the results.
So I just want to be sure if we needed to have something as strong as the Boolean prime ideal theorem to get here. So in absence, would we not have the?
No. So for this, we don't need the Boolean prime ideal theorem because we have a countable, even finite signature, and the completeness result just holds without any choice at all. So this is a theorem of Zermelo-Fraenkel set theory without choice. Yeah, as is compactness in the case of the countable signature.
Yeah, sure. The question is what you need in the meta theory.
Yeah. So we definitely don't need the Boolean prime ideal theorem. But for this, in the case of, for this result at all, we don't need that because we have a countable signature.
Excuse me if I'm not holding you up. Just one more detail. I'm interested about. I read about the apparent the reduction of the function of the functions in the model itself, and I'm just interested what are the proofs which verify that there isn't actually a problem, the model just gets reduced, if there are some formal ways of handling or demonstrating this.
I'm not sure I understand the question. Maybe we'll take this in the break.
Oh, of course.
Okay, so that's the Löwenheim-Skolem theorem. But as somebody's already said, there are, and I said there are stronger modern-day versions of the Löwenheim-Skolem theorem. And so the main goal of today's lecture is to prove one of those. So let me tell you what the downward Löwenheim-Skolem theorem is, which is the result that this is now seen as a very special case of. And the downward Löwenheim-Skolem theorem gives us much more information. And actually, I haven't prepared this, so I hope I get it right. Because I'm going to then go to a special. I want to give the most general result. The general result that's usually called the downward Löwenheim-Skolem theorem. A theorem, and we're not going to prove this theorem today, but just to let you know what it is, what's nowadays called the downwards Löwenheim-Skolem. So we've written their names once. I think it's enough to use the initials. The downwards Löwenheim-Skolem theorem says if you have a large infinite model, then within it you can find within that large infinite model, you can find smaller infinite models of any possible cardinality, where the cardinality, the lower bound on the cardinality is given by the cardinality of the signature. So this course, we're not going to assume you know too much about set theoretic cardinalities, which is why I'm not going to prove this result, but just so that you see it stated. So it says, let M be a structure over a signature. I can't remember what's over. Let's use L for a signature. Cardinality kappa, which is less than equal to the cardinality of the structure, but nonetheless greater than or equal to the maximum of Aleph 0 and the cardinality of the signature L. So this is saying, this basically says if we have any cardinality that's between the cardinality, any size that's between the size of the model and any infinite size that's between the size of the model and the size of the signature, and any subset X of M of cardinality kappa, then we can find a substructure of M of cardinality kappa that has all the same first order properties of that M had to begin with. So then exists what we call an elementary substructure, that's a substructure of the original structure that inherits all the same, that enjoys all the same first order properties. So there is an elementary substructure, M prime. So this symbol means an elementary substructure, is less than or equal with satisfying two conditions, that the set we started off X is also a subset of the domain of M prime, and the cardinality of the domain of M prime is kappa. Okay, so it's a bit complicated, but it says given an infinite structure and any smaller cardinality that's at least as large as infinite cardinality that's at least as large as the signature, we can cut down the original structure M to one of size kappa so that it still has all the same first order properties. But moreover, we can even do that in a way that we can incorporate any size X from the original structure of the cardinality kappa that we're heading towards. So we have, given a large structure, we have lots of ways of cutting it down to infinite smaller structures, basically. But this relies on understanding stuff about cardinalities that's beyond the scope of this course. So we're not going to prove this theorem. I'm going to, for this course, it's an important result. So for this course, the main result of today is going to be a baby version of this, which is easier to understand, but not that much easier to understand. I'm going to call this the countable elementary substructure theorem. This kind of, the result I'm going to give now is intermediate between the original Löwenheim-Skolem theorem and this downwards Löwenheim-Skolem theorem. So this is our goal result for today.
Can you recall what an elementary substructure?
So then, having stated this result, then we're going to then have a long stretch of development leading to the definition of what an elementary substructure is. Yeah, so indeed, I haven't told you what an elementary substructure is. It is a substructure that has the same first order properties. So this is then the main kind of really there are these theorems today like this, well, you know, the theorem, the compactness and Löwenheim-Skolem theorem are important, but really perhaps the more important content today is going to be the line of development that I'm going to start on soon, which is going to lead us to the definition of what an elementary substructure is. Yeah, sorry, I should have said that before. So indeed, at the moment, we're just understanding it as a smaller structure that has the same first order properties. Okay, so our goal theorem is going to be the countable elementary substructure theorem. Actually, it's going to be easier to just modify the. So let's you always run the risk of the cut and paste error when doing something like this. What would be the equivalent when you cut and paste and then modify something? But anyway, it should be all right. So so we'll rub off the title here. This is now going to be the countable elementary substructure theorem. So this is just my name. In most textbooks, you don't get this. In most textbooks, you get this. Anyway, so the theorem we're going to go is that M be a structure over a, let's put the changes in blue, over a countable signature. Then we have, and let X be the countable subset of the original structure. Then there exists an elementary substructure M prime of M, so a substructure that contains X and is countable. So let's just put countable there. Okay. With X being a subset of M prime. So whenever we have a large model over a countable signature, we can, and for any countable set X in the large model, we can cut down the large model to a countable model that contains the set X. And moreover, it's an elementary substructure. That means that basically we preserve the inclusion preserves all logical properties. And this is an interesting enough result. So let's, before going to the work leading towards the notion of what elementary substructure is, let's look at two examples. So one of them we've done before. So consider the reals with the signature that we were looking at when we did electron quantifier elimination for the reals. So we had addition, 1, and the order relation. This is, of course, an uncountable model, but it contains within it a countable substructure. It has to, by the countable elementary substructure theorem. And what is the countable structure within this that is a model? Well, one of them is just the rationals. And I did that at the end. This was one of the consequences of quantifier elimination that we showed in the lecture, in lecture 3 or 4, whichever one it was, 5 maybe. Is an elementary substructure. It's a countable. So the theorem in general tells us such a thing has to exist, and that in this case we can easily put our hands on such on an example of such structure. If we add multiplication, in which case we can define the order, then the rationals no longer work. But if we consider the algebraic numbers, then they form a countable elementary substructure. And the algebraic numbers. And we have a general existence theorem that tells us whenever we have an uncountable model, like we clearly do in these two cases, because we have the reals, we have a countable elementary submodel. But in some cases, we can quite easily find one. You find one for ourselves. But it's not so easy to find one in the case for oneself if one starts off with a model of set theory. And you take a large model of set theory as your large starting model, then it's not easy to just easily construct a countable submodel. So in that case, yeah, it's really important to have the general theorem that gives us the existence of such a model. And in fact, there are set theory is a big subject, but one important line of development is the style of proof called forcing, which in set theory, so it originated with Paul Cohen, who showed that the continuum hypothesis is independent from the axioms of set theory. It's neither provable nor refutable from the axioms of set theory. And nowadays, this element of the approach is no longer apparent in modern presentations of it. But the way he got to it was by thinking about if one has a model that refutes the continuum hypothesis, then one necessarily has to have a countable such model by the Löwenheim-Skolem theorem. And he started thinking along the lines that how can I understand countable models? And if I've got a countable model, perhaps then I can try and find a way to manipulate the model by forcing into the model, by adding it as an extra component to the model, a function, for example, from the real world that we know exists, but is not in our countable model. So this kind of line of thought that derives, that is based on the existence of countable submodels, actually turned out to be very important in the development of this aspect of logic. Anyway, so this is the countable elementary substructure theorem. So what we want to do now is set up the machinery that's going to allow us to understand what it means for one model to be an elementary substructure of another. Now I could do this in 5 minutes just by giving one definition. But actually, I think it's better to be systematic about it, because really this is an inclusion of one structure in another. So an inclusion, we've got this structure arises as a subset of this, but subset inclusions are just one example of functions. And just like in algebra, when you consider classes of structures, so classes of algebras, it's very important to consider morphisms between, or homomorphisms between the structures that preserve, between the algebras that preserve the structure. Again, in logic, we have our notion of structure is a bit more elaborate than in algebra. We've got we have the function symbols and relation symbols. But again, it's very natural to consider notions of morphisms that preserve the structure in different ways. And so the next thing I want to do is develop these kind of morphisms between structures. And the right level of generality to do it is now for an arbitrary signature, because what structures you have basically depends on your signature. So the structure has to have components that give structure for the function symbols and give structure for the relation symbols. So given a signature, so we'll have some predicate symbols. And some functions. So curly P is the set of predicate symbols here. And set of function symbols. Curly F is the set of function symbols. And we want to consider structures over the signature. And we want to consider structure preserving functions between the structures. So we'll first start off with just the simplest notion of preservation of the predicate and function symbols. So given two structures, curly M and curly M prime, and a function, we're going to consider functions that preserve the structure. So the function is going to be a function from the underlying set of curly M structure to the underlying set of the curly M prime structure. And we want to give various notions for what it means to preserve the structure. So the first one is simply preserving the signature components, and we call that a homomorphism, just like in algebra. So I'm using theta for the function just in order to distinguish it from the function symbols f. So theta is a homomorphism if firstly it preserves function symbols, and secondly it preserves the functions in the signature, and it preserves the relations in the signature. So for any function symbol f of arity k, and for all x1 to, well, let's use a1 to ak, so as not to confuse them with logical variables, of all a1 to ak in the structure M, for every function symbol of arity k, we have that if we apply theta, so just like a homomorphism for groups, say, if we apply theta to f interpreted in the structure M, applied to a1 to ak, and this is the same thing as f interpreted in the structure M prime, applied to theta a1, the tuple of arguments theta a1 to theta ak. And preservation of relation symbols. Again, if P is a relation symbol of arity K, then we ask for all A1 to AK in M, if in the structure M, P holds for A1 to AK, then in the structure M prime, P holds for theta A1 to theta AK. So it's the natural two conditions. One's used to seeing these conditions in many places, but not so often in practice in combination, because in mathematical applications, you tend to often either have structures defined in terms of some functions or structures defined in terms of some relations. So an example of a structure defined using function symbols only would be a group, where you're preserving composition and inverse and the identity element, which is a constant. And so in that case, you always get this condition here, that the theta is preserving the multiplication and the inverse and the unit of the group. And preserving the relation, one's used to seeing this, for example, in ordered structures like partial orders, where this would be an order relation in one structure and an order relation in the other, and this would be the monotonicity or increasing property, this implication. And just for a general structure that combines both function symbols and relation symbols, it's natural to have these two conditions.
Here we have a theta acting on the a's on the one hand and on the other hand on the function symbols. So we're strictly speaking.
No, it's just acting on the a's. So theta. Have I written something wrongly? No. So theta is a function from the underlying sets.
Yeah.
And here the function symbol is a function, so it gives us back an element of the underlying set. So here we're applying it to an element of the underlying set. Yeah.
The function symbol is interpreted, so it's not a function symbol, it's a genuine function.
Yeah, sorry, this is indeed the genuine function in there. Yeah, it's interpreted in the structure. Good, thank you. And just to say, equivalently, it's very easy to see. Equivalently, instead of these two bullet points, we could say this, which is for all environments rho, and atomic formulas M environments of variables in the structure M. If A is true in M under the environment rho, then A is true in M prime under the environment theta composed with rho. Okay, which gives us an M prime environment. So being a homomorphism is the same thing as preservation of logical theta preserving the truth of logical formulas. Of atomic formulas, in general, atomic formulas, including atomic formulas with variables.
Excuse me, should perhaps the M prime model also be?
Oh, sorry. Thank you. That should be the M prime model. Yeah. Okay, that's a homomorphism. Slightly stronger notion. So say theta is an embedding if it is a homomorphism and also It's also injective. Well, let's just make that an injective homomorphism. And also, we strengthen the preservation of relational properties to an if and only if. So for all k array relation symbols and for all A1 to AK, P holds in M for A1 to AK, if and only if P holds in M prime for theta A1 to theta AK. So once again, this is familiar given standard usage. For example, we used the notion of a subgraph earlier when we were talking about the De Broglie Erdos theorem. A subgraph is exactly a graph that embeds in the larger graph. An embedding there means not only do we map edges in the smaller graph to edges in the larger graph, but also if we map two vertices in the larger graph and there's an edge between them in the larger graph, there needed to be an edge between them in the smaller graph. The smaller graph inherits the edges. And that's exactly this reflection, this if and only if property here. And once again, we can characterize this as preservation of formulas. It's the same as asking for this to be an if and only if. So the preservation of atomic formulas becomes an if and only if here, but we can make a nicer statement, which is now equivalently for all M environments rho and quantifier-free formulas A. Quantifier-free formulas have been important in several places already in the course. We have this preservation. So if the quantifier-free formula is true in M under rho, then it holds that the quantifier-free formula is also true in A under the composite environment theta composed with rho. And just to say, another equivalent statement is the same as this, but we replace the implication here with an if and only if. So here we're asking for the function to preserve logical properties, and here we're asking for it to preserve and reflect the logical properties. These two are the same. Can somebody give me a reason for that? And then we'll have the break. Just to see that you're on your toes, so to speak. Yeah. So this implication holds for all formulas A. Look, quantifier-free formulas A is the same as the if and only if holds for all quantifier-free formulas A. Okay, well, maybe it's a good point to have a break, and you've got something to think about in the break. But by the clock on the back wall, it is 6 o'clock, so we'll start again at 7 o'clock. No, not 7 o'clock, 6:15. Notion of homomorphism, which amounted to preservation of atomic formulas, of the truth, the function preserves the truth of atomic formulas, and then embeddings, which is preserving more generally the truth of all quantifier-free formulas. And I commented that that's the same as preserving and reflecting the truth of all quantifier-free formulas. Has anybody realized the reason for this? It's not to do with injectivity.
No,
I mean,
it can only have property above, right? I mean,
well, it's yeah. There's that. Okay, so I mean, it can be. You can obtain it from injectivity together with the property above and sort of work by induction on the structure of the quantifier-free formulas. But the easier argument is just from this. It's just simply the observation that formulas are closed under negation. Atomic formulas, sorry. Quantifier-free formulas are closed under negation. So if you've got the implication in one direction for A, you have the implication in the other direction for not A. So it's simply that observation. Because this is for all formulas and they're closed under negation. So the implication in one direction is the if and only. Okay, so once one's observed this, there's a very obvious natural strengthening of the definition, which is just to drop quantifier free, because then you're asking for preservation of all first order properties. And unlike the other conditions, so the other conditions we gave direct, the other properties, homomorphism embedding, we gave direct properties that say exactly what it is first and then characterized it in terms of logic preservation. If we're preserving arbitrary formulas, there is not really an easier characterization than preserving arbitrary formulas. So we're going to use that as the definition. And this is the notion that's known as an elementary embedding. So this important definition. So theta is an elementary embedding if definition, so we need if and only if, but we just say if. So if and only if for all M environments formulas A, so arbitrary formulas in our language, we have the implication that if A is true in M, then A is true in M prime under the environment theta composed with rho. Or equivalently, so equivalent symbol Ly, we've had this in a previous lecture, but just to explain it again, equivalently the same quantification and an if and only if, because again, formulas are closed under negation. And this is a very important class of maps between structures. Functions that preserve and hence reflect also all first order properties. Between formulas, so including interpretation of formulas of variables by elements of the model using the environment, or another way of saying that is first order properties in parameters taken from the model. Okay. And once we've got the notion of elementary embedding, an elementary substructure, be the case in which you have an elementary embedding and the theta function is a subset inclusion function. Okay, so if M is a subset of M prime, the underlying structures, and the structure M is an elementary substructure of M prime. Notation which we've used already in the statement of the countable elementary substructure theorem. If the inclusion function from M to N prime is an elementary embedding. But I won't write it down because this is going to be the topic of next week's lecture. We also say that M prime is an elementary superstructure of M. Okay, but this is the notion of elementary substructure. So we now finally have the notion of elementary substructure from the theorem. But really, it's this property that clarifies what we mean by preserving first-order logical properties. And we have various notions of map between them: homomorphisms, embeddings, and elementary embeddings. All three of these form categories. That's the various kinds of morphisms compose. So composition of two homomorphisms is a homomorphism, of two embeddings is an embedding, of two elementary embeddings is an elementary embedding. When you have a category, it's natural to ask what the isomorphisms in the category are. In all three cases, the isomorphisms are exactly the same thing, and they are just what we would call isomorphisms. So let's just remind you what an isomorphism is. So theta is an isomorphism. So again, it's our theta from M to N prime. If the function theta from M to N prime is a bijection, which means it has an inverse, which is a function, and theta minus 1, its inverse, are both homomorphisms. For those of you who are used to algebra, you might be used to the situation that if you have a homomorphism that's a bijection, then its inverse is automatically a homomorphism. That, for example, holds in groups, between groups. That's not the case here. So in our case, we really need to require both theta and theta to the minus 1 should both need to be homomorphisms. If we go to embeddings, then probably things get better. I guess, yes, it should be. Anyway, so the notion of isomorphism is defined in terms of homomorphisms, but proposition, and this is really tedious to prove, so I'm not going to prove it, is that every isomorphism is an elementary embedding. You simply prove the required preservation property using the isomorphism property. You simply prove it by induction on the structure of the formula. So it's tedious, but this is a really important result. If this didn't hold, somehow there would be something wrong with our logic. Because logic is about presenting, if we've got our structure and the logic is giving us a language for expressing properties of the structure. For those properties, the important properties, it should be irrelevant what the names of the elements of the structure are. So if we rename them, if we rename the elements of the structure, then the properties should stay exactly the same. And they do, and that's, you know, renaming is basically transforming the structure along a bijection, and the fact that we get an elementary embedding is saying that the properties stay the same. Okay, while we're at it, before going to the proof of so the last thing I want to do is the proof of the countable elementary substructure theorem. But before going to that, I just want to mention one other thing, and here we're talking about functions between structures that preserve logical properties. Even independently of considering functions between structures, it makes sense to ask, do two structures have the same logical properties in terms of sentences? And in fact, we can think of logic as a way of distinguishing between different structures. So, for example, the field of rational numbers would be distinguished from the field of real numbers by the logical statement that says 2 has a square root. Okay, so it's a logical property distinguishing between two structures. So it's natural to wonder how rich a language first order logic is for distinguishing between two structures. And because of the elementary substructure theorem that we're going to prove, it means somehow we can't distinguish. We take a large structure, we find a countable substructure within it, and because we have an elementary embedding, those two structures have the same logical properties, so they, in particular, the same sentences hold, so there'll be no logical property that distinguishes between those two structures. Now, those structures are kind of equivalent in the sense that we can't distinguish between them using logic. So that's an important notion of equivalence. So this is now slightly off track because it's not directly about morphisms between structures, but it seems an appropriate point to bring it in. So we say two structures M and M prime are what's it called, elementary equivalent. And the notation for that is simply one uses that equivalence. I mean, you obviously need to be in the context that you know you're talking about logic, but then this means elementary equivalence. If the sentences true in M are the same as the sentences true in M prime, or in the terminology of lecture 2, the theory of M is the same as the theory of M prime. And it's immediate from the definition of elementary embedding here that if you have an elementary embedding from M to M prime, then M and M prime are elementary equivalent. So note NB, nota bene, note well, if there exists an elementary embedding of M in M prime, then M is elementary equivalent to M prime. And yes,
in these two sets, there are just sentences, right?
Yeah, the theory is the set of sentences true. This was lecture 2, I think. So one thing I should have said earlier. So today the LaTeX notes are, unlike last week, the LaTeX notes today are quite comprehensive. The only thing missing from the LaTeX notes is the application to the De Bruijn-Erdős theorem. But I should have actually told you at the time that that wasn't going to be the latex note, so you know to sort of particularly carefully take notes, because anyway, sorry, I forgot to do that. But anyway, so the latex notes today are fairly comprehensive. At the end of the lecture notes, there are lots of exercises about relations between these structures. Maybe some of them will be done at the exercise classes next week. In particular, there's a hard exercise at the end that I've had in for years, and it says there's a challenge question, and if anyone can solve the question, please let me know, because I'd like to have a nice answer to this question. Nobody has ever come to me with an answer. So anyway, fingers crossed this year. If you want a challenge, there is a challenge question at the end of today's lecture notes. Right, so the last thing I want to do is prove the elementary embedding theorem, the countable elementary substructure theorem. So we've got a large model, and the theorem says we can cut it down to a countable submodel. Moreover, we can do that in such a way that given any countable set in the original model, we can include that countable set in the submodel. So there are going to be two steps to this. One is going to be the main proof that does the cutting down process. That's the more interesting part. But in order to get the result, we're going to use what's called we're going to use a lemma, which gives a simple practical test for showing that a subset gives us an elementary substructure of a larger structure. And this is a well-known result. It's called the Tarski-Vaught test or Tarski-Vaught criterion. So I'm going to state that first and then use it to prove the main result. So in the notes, this is down as a lemma. So Tarski-Vaught criterion or test. Suppose let me just check in the notes which way around n and n prime are, just to be consistent. This is that the structure n embeds in m prime via the inclusion map. So it's an embedding, but we don't know that it's elementary. Is an embedding. And that embedding is an elementary embedding. So this is the symbol for being an elementary embedding. If and only if existential formula exists XA and M environment rho, it holds that, or we have that statement is true in is true in n prime, if and only if there exists an A in M such that X is A, such that A is true for that element, little a. Let me just check thing is that an existential statement is true in the larger model. An existential statement in which the variables in A are interpreted by elements of the smaller model, but the existential statement is made in the larger model. That's true in the larger model if and only if there's some witness in the larger model for the existential statement that actually lives in the smaller model. Okay, so every existential statement in the larger model, where the variables all live in the smaller model, is witnessed by a witness from the smaller model. Okay, the right to left implication here is trivial because it's immediate from the semantic definition of the existential quantifier. Is the left to right implication here that's here we're just guaranteed there exists something in the larger model, and here that requirement needs to give us that actually there always also exists something from the smaller model. Yeah. Are you? No, absolutely respecting. Yeah. Okay. So I'm going to leave the proof of this because it's actually easy. It's just by induction on the structure of formulas, and you can look it up in the LaTeX notes. So it's homework to understand this proof, and you can also work it out for yourself.
Doesn't because rho is an M environment?
Yeah.
Doesn't it by definition only map to elements of M?
Yeah, rho only maps to elements of M.
Yeah.
But we're requiring that if in the larger model the existential statement is true,
yes,
so then if this holds, even though rho maps to smaller elements, for the existential statement holds in the larger model, there's nothing to tell us that it should hold for a witness from the smaller model. It just holds for some witness from the larger model. So the condition here is that when this holds, it has to also hold a foot even more strongly for a witness from the smaller model.
Okay, I got questions, but let's go.
Yeah, it's correct. That's formulated. So I want to stick to the essence in the proof of the countable elementary substructure theorem. The proof of the countable, as I call it, elementary substructure theorem. Central European summertime. That seems appropriate. The first week that it actually was appropriate. And there we go. Right, so I should remind you of the statement of the theorem, but let's just do that by making the relevant assumptions that we need in the proof. So suppose, so M, I don't remember which one was M and which was M prime.
M was larger.
M was larger.
Yeah.
Oh, it's going to be M prime. So
Here M prime is also larger.
yeah, well, so now M prime is going to be larger. So suppose M prime is infinite, and we're assuming a countable signature, and X, which is a subset of M prime, is countable. And what we want to do is construct an elementary substructure of M prime that's a countable elementary substructure of M prime that contains X. So what we're going to do is we're going to approximate the underlying set of M prime in stages, starting with X and then adding the elements that we're forced to add in order to get an elementary substructure. And when are we forced to add an element? Well, we're forced to add elements so as to fulfill this Tarski-Vaught criterion. So whenever we have an existential statement, we're going to want to witness it with by adding an element satisfying that. So we define in sequence, we define a chain x0 subset of x1, x2 of subsets of n prime. Well, we start off, of course, with x, for x0, and then we need to define xi plus 1. So xi plus 1 is everything in xi, together with all elements we need to witness existential statements whose parameters are taken from the set of things we already have, so namely xi. So we add D, where all elements D, such that the following holds. So we've got well, let's just write it like this. We've got some formula. Maybe, so in the notes I use X, but let's, for clarity, use Y here. So here, X is a vector of distinct variables containing the free variables of this existential formula. Is a formula. And we're going to give ourselves some, so let me use E here. We're going to give ourselves a vector of elements D in xi to interpret these parameters x, these are variables xi. So D is a vector of the same length, vector of elements of xi, let's put it here, of the same length as x. And we're only interested in cases in which this formula is true in M prime with the x's instantiated by the d's. So we want it to be true in M prime that exists y A holds for the environment of it's not really enough space there. Let's put the environment down here. So we extend row. Sorry, we don't have a row. We make the environment that interprets all the x's. The vector of x's is interpreted as the vector of d's. The point is we've instantiated the free variables of A with elements from xi. And lastly, E is a chosen element of the underlying set of the large structure N prime, such that the formula A is true for, we interpret the x's as the d's again, we interpret y as E. So we interpret this as the d's and the y as the E. Okay. Okay, so it's a bit complicated, but the idea is not so hard. It's for every existential formula whose parameters are taken from xi, from the previous set xi, which is true in the larger structure. We choose a witnessing element, so we're using some choice here, but actually, as long as we can enumerate the set in some way, it's, yeah. Anyway, it doesn't. Let's ignore issues of choice. we're choosing some element of E, which witnesses that existential statement, and we're adding that to our domain xi plus 1. And we keep on, and we do that. Yeah. So xi plus 1 contains all the witnesses for the true existential statements that have parameters in xi. But then we get some new, potentially true existential statements that have parameters in xi plus 1. So xi plus 2 will contain witnesses for those, and so on. And we make the observation, let's just carry on the bottom half of the board here. So every xi is countable because there are only countably many existential formulas. Here we've got a finite vector of elements taken from, by induction hypothesis, a countable set xi. So only countably many ways of instantiating those. And then, only some of those things will give rise to a true formula. That's cutting it down to something smaller. So we've got only countably many such formula vector combinations that give rise to true formulas. And for each of those, we choose exactly one witness. Okay, so there are countably many chosen different witnesses we're throwing in. So each of the xi's is countable. Hence, the countable union of countable sets is countable. So hence, the union, hence x infinity, which we'll define to be the union of the xi's, is countable. And now we verify that x infinity defines a countable elementary substructure of M prime. Now, this verification is done in the LaTeX notes. I don't really want to write it down on the board. Let me just tell you what there are two parts to this verification. The second part is to verify the Tarski-Vaught criterion. Okay, so that the inclusion function gives us this Tarski-Vaught criterion, and that is straightforward because we've built that into the construction of the set x infinity. For any existential formula, true in the larger model, that has a vector of parameters from x infinity, well, there's a finite vector of parameters, so that finite vector comes from one of the xi's, and then the xi plus 1 will contain a witness to the existential statement. So the Tarski-Vaught criterion is built into the construction. But there's something else we need to verify first before we get to testing this property. Can somebody see what it is? Fill this top line that we've got an embedding, okay?
Is it the interpretation of function symbols?
Indeed. So, yeah. So what we've got to do is we've cut down to, it's exactly that. So cut down to a subset. We need to show that we've got a substructure which embeds. So a substructure, we need to interpret both the function symbols and the predicate symbols on it. It's easy to cut down the predicate symbols because you can always cut down predicate symbols to a subset. You just say the predicate symbol holds of elements from the subset if it held in the larger structure. But the function symbols, you've got the problem that when you cut down to a subset, the original function symbols might take the elements somewhere else outside the subset. So potentially then we would have to start closing this under function symbols. But that doesn't happen because the value that a function symbol maps to can be, you have for the function symbol, if you apply it to some arguments x1 through to xk, you have a formula in parameters, and you've got the existential statement there exists a y that the function symbol maps to, that f of x1 to xk map to. there's exactly one witness to this, and by this construction here, we're forced to throw that witness into the model. Okay, so the function symbol, so the values of function symbols automatically get thrown into the model. Okay, so that's basically the idea of the proof of the countable elementary substructure theorem. There's also the proof of the Tarski-Vaught criterion, but I think, you know, that, as I said, think about it, prove it for yourself, and if all else fails, you can read the proof in the notes. I think that's enough for today. Are there any questions?
Yeah.
Yes?
Is this like, is the full proof examinable material? Are we expected to know the thing that you didn't write down?
Well, I've told you that you should know it. Yeah.
Okay.
It's not very hard. So it's the sort of thing, if you understand the material, you can't. This is the kind of, when if you understand the definitions, it's a follow your nose proof. This one. So it's not. It shouldn't be too hard. But this is for the oral exam. Anything else? Okay, so see you next week.
Really don't want